Log on, tune in, find out. Another good idea from Cambridge.
About divide categories and perverse sheaves.
Okay, thanks. Maybe I'll start by reminding you of something that came up yesterday in the discussion section. I talked about an example of a local system, and the definition was like this. We got a local system on the space, which is the complex plane minus the origin, and it was defined this way. So it was a sheaf whose sections over an open set U were defined to be solutions of the differential equation x df dx equals 1/2 f of x. Okay, over U. Okay. So what I want to talk about today is sort of a vast generalization of this idea, the idea of getting local systems as solutions of solution spaces of differential equations. So the first thing I want to do to sort of work on generalizing this is introduce some setting in which we can talk about differential equations in some more generality. So I want to make a ring, which is going to be called D, and it's going to be a non-commutative ring generated over the complex numbers by two elements, which are just formally called x and d by dx. And I want to think of both of these as operators on functions. So d by dx is just the usual derivative, and x is a variable, but this is supposed to be the operator which multiplies a function by x. So of course, multiplying by x and taking the derivative don't commute. So this is non-commutative, and it's easy to work out what happens, what the commutator of these is. Let's see. So I guess this is some basic thing from calculus. If you take a function and multiply by x, and then take the derivative, that should be x times the derivative plus f of x. So in D, so what I want to do is just erase all the f of x's from this equation. So in D, the commutation relation between these two elements that generate it is d by dx times x equals x times d by dx plus 1. Okay. Okay, so this is a ring, and so of course modules over it are called D modules. So throughout this talk, so of course, since it's non-commutative, you have to distinguish between left and right. And so throughout this talk, I'm going to stick to left D modules. Okay. And now this differential equation from yesterday, we could take the operators in that equation, and that's an element of this ring. So let P be that element. So x d by dx minus a half. So that's an element of this ring. Okay. Okay. So let me introduce a bit more notation. So let O be the ring of holomorphic well, I might change the meaning of O from time to time. So let O be the ring of holomorphic functions of one variable. And then, yeah, well, I guess I need to change it right away, actually. So let's make this be the sheaf of holomorphic functions on the complex plane. Okay. Well, anyway, I guess it'll become clear in a moment why I wanted to do that. And then, so D acts on, well, O of U for any open set U. So O of U just means the holomorphic functions on U. So of course, you can take a function and multiply by x, and you can take its derivative. And those two operations obey this relation, well, precisely because we figured out this relation by making sure that it's obeyed. And then to say that something is a solution of that differential equation, let me go up here and label this. So I'm just writing some elementary things in a couple different ways right now. So a function f of x is a solution of that differential equation if and only if, well, f of x is an element of one of these spaces, and this ring acts on it, and in particular, this element kills f of x. So if and only if pf equals 0. Okay. Okay. So here's another way to say this. Let's consider the module which you get by taking D and modding out by the left ideal generated by P. Okay, so this is going to be a left module over D. Then I want to consider the space Hom M O U or something. Okay. So what does it mean to give a this is going to be Hom of D modules. So what does it mean to give a map from this module to this module? Well, M is generated as a D module by one element, by the image of the ring element 1. And so of course I can specify an element, a map mu from M to O of U by telling you just what mu of 1 is. Okay, so if I give you one function, then that determines the map. And I can't just give you any function. That function is subject to a constraint because, well, the element 1 in M is killed by left multiplying by P. So it has to satisfy the condition that Pf equals 0. So in other words, in other words, in other words, elements of this Hom group, Hom D M O view, are exactly the same as solutions of the differential equation. What was it? X df dx equals 1/2 f of x. Okay. So if I have a solution to that differential equation, then I can define a map like this, and conversely, if I have a map, I can pick off mu of 1, and that's a solution. But the advantage of looking at this side of this picture is that, well, already the way I've written things, I'm sticking in different groups here. I can change u, and I'm looking at a different space of functions. You could look at, well, you can replace OU by other function spaces. Well, for example, you could look at only polynomials. If you wanted to get polynomial solutions to a differential equation. You could, well, I guess here I put the word holomorphic. You could, oh, I guess I have the complex numbers throughout. If you had real coefficients, you could talk about maybe real analytic solutions instead, or C infinity solutions. You can put in different function spaces and get different kinds of solutions to the differential equation. And so the idea that I want to extract from that is that the D module itself, M itself is a kind of universal solution space to some differential equation. Okay. All right. So now let's make everything much more general. Okay. So now instead of a specific ring of differential operators in one variable, I'm going to start with this setting. So X is going to be a complex manifold. And then, so I guess in the example we've been talking about, X was just the complex numbers, but now you can take any complex manifold. And then script D of X is going to be the sheaf of partial differential operators on X. So locally, this is going to look like the ring that I wrote up earlier, except there'll be many variables if this has dimension bigger than 1. And then now by dx module, I'm going to mean well, this is going to be a kind of sheaf on X, which which over each open set is a module over the ring of differential operators over that open set. So, and then O of X is now going to be the sheaf of holomorphic functions. on X. Okay, so you know, we've been doing a lot of stuff with derived categories. And so, well, what we did earlier to talk about solutions of differential equations was take this Hom group. So now let's well, while we're generalizing everything to higher dimensions and sheaves and stuff, let's also simultaneously pass to the derived category. So we're going to replace that Hom by an R Hom. So here's the derived version of the sheaf of solutions to a differential equation. So we're going to take R Hom, and it's going to be sheaf R Hom. It needs to be sheaf R Hom because, well, we already ran into this problem just in that tiny example in one variable. You might have solutions over some open set that don't extend to a bigger open set. So you'll miss stuff if you don't take the sheaf R Hom. So sheaf R Hom is going to be something where you plug in a D module in the first variable, which is some kind of universal set of solutions to a differential equation. And then when you take R Hom into the sheaf of holomorphic functions, that'll give you the sheaf of holomorphic solutions to that differential equation. And then so this operation, this is a functor from, well, the thing you plug in here should be a complex of D modules. So this is an object in the bounded derived category of dx modules. And then, well, what do you get out of that? Oh, this is R Hom over dx. And this, and of course, it makes sense to say that that you're taking R Hom over dx because OX is a dx module. And then, well, we'll see in a moment what we get here. But to start off with, we could just say that you get a sheaf of vector spaces, or rather a complex of sheaves of vector spaces. So this is chain complexes of dx modules, and this is a chain complex of sheaves of vector spaces. Okay. Okay. So the first thing we want to do is, well, I guess so. Arun told us about two theorems from linear algebra. So one theorem from differential equations that you learn as an undergraduate is that you know, under suitable conditions, the solution to a differential equation with initial conditions or whatever is unique. And then maybe a fancier way of saying that is that this Hom space is finite dimensional. In this case, it's just one dimensional. And that's, well, that's a nice property. That's something that we'd like to see how to achieve in higher dimensions. The problem is that if you just write down a partial differential equation in several variables, it can easily happen that the solution space is infinite dimensional. So to get this functor R Hom dx OX to be well behaved, and the first thing I mean by well behaved is that the solution spaces should be finite dimensional. So let's understand exactly what solution space means here. You get a complex of sheaves of vector spaces. So when you take a cohomology sheaf for that, I want those sheaves to have finite dimensional stalks. So the stalks of the cohomology of the output of this functor should be finite dimensional. Okay. So we need to impose a condition. And this condition is called is called holonomic. So I'm not going to write down precise definitions for most of these things because I want to get to an application of D modules in representation theory by the end of today. But roughly a holonomic D module is something that corresponds to an overdetermined system of partial differential equations. Okay. So holonomic is some technical condition, and then when you impose it, it turns out that the thing that we wanted that I wrote up on the board above happens, but in fact something more happens, and this is a result of Kashiwara. So if M is a holonomic D module, dx module, then the sheaf, or rather the complex of sheaves that you get by plugging M into this functor, it has finite dimensional stalks, just like we wanted. But it also has a feature that showed up in the example from the very beginning of the talk, where the space of solutions formed a local system. This might not form a local system, but it's going to be something close enough to a local system. It's going to have constructible cohomology sheaves. So just to remind you, constructible means that there's some stratification such that on each stratum, the restriction of the cohomology sheaves to those strata are local systems. So restrictions to strata are local systems. Okay, so in other words, this functor, let me maybe modify this statement of what functor we're looking at right here. So I'm going to add a little subscript h to this, which is going to mean that we're looking now not at the full bounded derived category of dx modules, but the subcategory where the cohomology sheaves are holonomic D modules. And then I'll add a C here, and this means the same thing as yesterday. So this means that the cohomology sheaves are constructible. Okay. Okay. So we can make one more refinement to this. And the refinement is this. Instead of looking at all holonomic D modules, if we look at only the ones that obey a condition called so here's the restriction. So we're going to restrict to dx modules with so-called regular singularities. Okay, so this is some condition that you can phrase really in just in elementary language of differential equations, and then here's the big theorem that comes out of this, and this is also Kashiwara. I guess the analytic version of this. I've been stating things in analytic language. The analytic version is due to Kashiwara, and maybe the algebraic version is due to Balance and Bernstein. And it says that the functor Arham with OX, so we're going to take just that functor that's up there, but I'm going to add another subscript here, RH. So this is going to be now regular holonomic D-modules. And that takes values. Well, we already know it takes values in the bounded derived category of constructible sheaves by Kashiwara's other theorem. And then this turns out to be an equivalence of categories. So this is an example of a derived equivalence. This equivalence of categories is called the Riemann-Hilbert correspondence. This was something of a mystery to me because Riemann, of course, was active in the middle of the 19th century and Hilbert around the turn of the 20th century. And neither D-modules nor derived categories were defined until the 1960s. So what sense does this make? But the sense it makes is that this is really something about differential equations. And it turns out that, this has to do with Hilbert's 21st problem, which is roughly the following. So this is Hilbert's 21st problem, and Hilbert, in his statement of the problem, attributes the problem to Riemann. And the problem basically says, given a specified local system, and of course he didn't use the language of local systems because sheaves were also not defined until the 1940s, maybe. But it's equivalent to saying, given a specified local system, show that there exists a differential equation whose solutions give you that local system, or form that local system. So that's something like saying, well, Hilbert's 21st problem, sort of a much generalized and fancified version of it is saying, show that this functor is surjective. So anyway, so it turns out that it's not just surjective, it's an equivalence of categories. So now that we have an equivalence of categories, one thing you can ask is, well, there's a T structure on this derived category. Any derived category of an abelian category has the natural T structure where the abelian category you get is the abelian category of regular holonomic D-modules. So in in dBRH dx, we have the natural T structure, which gives you the abelian category of regular holonomic dx modules. And then you can sort of follow that T structure across the equivalence. And we know about two T structures on here already. We know about the natural one, which gives you the abelian category of constructible sheaves. And then we know about this rather more complicated one, which gives you the abelian category of perverse sheaves. And then the remarkable thing here is that it's the second one that you get through this equivalence. So when you follow this through the Riemann-Hilbert correspondence, you get the perverse T structure on dBcx. So perverse sheaves, of course, well, they have plenty of applications, and they come up in lots of different ways. But this specific result is often cited as evidence that sort of perverse sheaves are really, even though the definition is something quite complicated looking, they're already there in nature. They're what you would come up with if you went on long enough with your undergraduate differential equations class. Okay, so okay, so now let me sort of switch gears and try and connect this to some representation theory. So here the setting is going to be that G is a complex reductive algebraic group. This is its Lie algebra. Well, I want to talk about representations of the Lie algebra. And the first thing you can say is that, well, G, I mean, what are elements of G? Elements are tangent vectors, or maybe they're left invariant vector fields on the group. And, well, vector fields are, well, they're things that act on functions as differential operators. So this is the first hint that Lie algebra representations should have something to do with differential equations. I'm mentioning this only sort of for motivation and intuition. It turns out that working directly on G is a bit too big. So we want to switch to a smaller variety to really make a link between Lie algebra representations and D modules. And here's how we're going to do that. So the first thing I want to do is switch from the Lie algebra directly to modules over the associative algebra, which is the universal enveloping algebra. And well, of course, if you have an irreducible representation of the universal enveloping algebra, the center has to act, well, elements of the center have to act by scalars. And that data is called a central character. So let's fix a central character chi, and consider only those UG modules where the center acts by chi. So the center of UG acts by chi. Okay, so one fact about making this restriction is that, well, right away you find out that there are only finitely many irreducibles with this property. And of course, G itself has infinitely many. So
Do you mean category O?
yes. Yeah, so I guess I should say B finite. What else am I supposed to say? Okay, yeah. So I'm thinking of B finite UG modules.
Well, H diagonalizable.
Sorry?
H diagonalizable.
H diagonalizable, yeah.
And then perhaps you want parallel subgroup of the group.
Yeah, so, okay.
I mean, if you want parallel subgroup, then your character should be integral.
Yes. Yeah. Yeah, I guess that's enough. Okay. Okay. So let's form a quotient of u of g just by identifying every element of the center with the scalar that it's supposed to act by according to the central character. So a central element is going to be equal to its character value, which is a scalar. And then here's the theorem. This quotient of u of g is the global sections of something like dx on the flag variety g mod b. Not exactly. It's some slight modification that depends on the central character. But anyway, it's closely related. And then there's more. This is, I guess this is also, both of these are due to Balance and Bernstein. There's an equivalence of categories between, so u of g modules with all these assumptions above, so h diagonalizable and b finite, with the specified central character, and the category of d modules over the slightly modified version of d. So d chi g mod b modules.
Chi should be regular.
Chi should be regular. Okay. Yeah.
And then, well, why don't we just put chi equal to what is called 0?
Yeah, that's what I'm about to do.
Keep condition of being finite. Well, and then this should be true. Okay. So yeah. So with chi, well, with the sort of trivial central character, this turns out to be just the ordinary g mod b, not modified in any way. And then so later on, I'm going to come back just to this case. Although much of what I'm going to say makes sense in greater generality. So I'm going to put this aside for a while, and then tell you what the Kazhdan-Lustig conjectures say. Okay, so let W be the finite Weil group of G. And then yesterday in Meinolf's talk, we learned about the bases called TW and CW for the Heck algebra. And so, of course, you can write one basis in terms of the other. And then the Kazhdan-Lustig polynomials are the coefficients so these I'll call P, Y, W. So the subscripts here, Y and W, are both elements of the Weil group. And these are the coefficients for the CWs in terms of the TWs. And then this is probably also slightly wrong because there are the C's and the C primes and the T's and the T tildes. So I'm not going to write down any formula, so it's OK if I don't worry about that. Okay, so so for the trivial central character, well, the modules that come up, the irreducibles are the highest weight modules of this form, minus W rho minus rho. So rho, as usual, is the half sum of the positive roots. Yep. I think this is correct. Okay, so there are irreducibles whose highest weights are these, and this category. So the category of UG modules we're looking at contains these irreducibles, and it also contains Verma modules with the same highest weights, which I'll call M minus W rho minus rho. And then you can take a Verma module and write a composition series for it in terms of irreducibles. So let AYW be the multiplicity of L minus Y rho minus rho. Let me make sure I'm getting this right. In a composition series for M minus W rho minus rho. Okay. Okay, then the conjecture is that, well, if you take the matrix of all the AYWs, so this is a matrix whose rows and columns are both labeled by elements of the Weil group, then the inverse of that matrix is given by taking the Kazhdan-Lustig polynomials, which come from the structure theory of Hecke algebras. So those are polynomials. Those are, I guess, they're, well, in principle, they could be in this ring of Laurent polynomials. Evaluate them at 1, you get a matrix, and then that's the inverse of this matrix of multiplicities. Okay. So here's an outline of the proof of this conjecture, which sort of combines a lot of the things we've talked about over the past couple of days. So this has to do with the geometry of G mod B. So, and we're going to sort of pass through D modules and perverse sheaves to put all this together. So stratify G mod B by B orbits. So this is the Bruja decomposition, which Arun told us about. I'm going to name the orbits things like XW, and those are indexed by elements of the Weil group. And then, well, once you've done the stratification, well, let me mention that all the XWs are simply connected. In fact, maybe one way of saying the theorem that Arun was proving in his talk is that, well, he wasn't talking about the finite flag variety, but these are in fact just copies of affine space. So these are some ANs. So the fact that they're simply connected means that there are no non-trivial local systems. Okay, so so what we could do is compute all the all these IC objects, the simple perverse sheaves. So I'm going to take an XW, take the trivial local system, which is the only irreducible local system there is, restrict it to another B orbit in its closure, and then record the result as a polynomial, just like we did at the end of my talk yesterday on the nilpotent cone. And well, what polynomial do you get? The theorem of Kazhdan and Lustig is that these polynomials, these are basically the Kazhdan-Lustig polynomials. You have to make some sort of trivial adjustments. If I got this correct, you have to replace x by x squared and stick an x to the minus L of W in front. Although, I mean, I guess exactly what formula this is depends a little bit on how you normalize these polynomials. I think this matches with the way I wrote the polynomials yesterday, but anyway, this is approximately correct. And then now we're basically ready to put everything together. Okay, so here's sort of the diagram of ideas. So first, we've got the Heck algebra of the Weil group, and that gives rise to the Kazhdan-Lustig polynomials. And then the Kazhdan-Lustig conjecture says that these polynomials have something to do with the structure of certain U of G modules. Namely, multiplicities of simple U of G modules in those Verma modules. And here's what else we have. We have this theorem of Kazhdan-Lustig that says that these polynomials are related to perverse sheaves on G mod B. So that's Kazhdan-Lustig. We have the Riemann-Hilbert correspondence, which gets us between perverse sheaves on G mod B and D modules on G mod B. So that's Riemann-Hilbert. And then we have the Beilinson-Bernstein correspondence, which gets us between D modules on G mod B and the appropriate category U of G modules. So maybe this picture simplifies things a bit too much. Just following this diagram around doesn't quite prove the conjecture, because you still have to figure out, well, these polynomials are telling you the structure. They're telling you about the structure of certain perverse sheaves. So when you follow that information across the Riemann-Hilbert correspondence, what exactly does it tell you about D modules on G mod B? What does it mean to plug one into the polynomials? So there's still work to be done here, but this is the basic idea, and this was done separately by Beilinson-Bernstein and by Berlinski and Kashiwara. Okay, so yeah, so maybe I'll just stop there for today.
Any questions? Not. We'll have a half-hour break. Start again at 11:30.